So now let's move to, so we went very basic concepts and definitions, structural analysis. Now let's move to field examples with the Alpine Himalayan belt. So that's a topographic view of the Alpine Himalayan belt from Gibraltar all the way to Tibet and Indonesia, going across the Alps, the Taurides in Turkey, the Zagros, and so on. And you see very different topographic features. The wedge shape, triangular shape mountains in the Western Alps. The Himalaya Tibet represents a plateau, flat plateau, with an altitude average 4,000 meters. And the Aegean, wow, where are the mountains? There's a hole in the mountain here. That's going to be a big question. How come in a zone of plate convergence there is a hole in the mountain? And these topographic features formed in the same kinematic environment. There are some slight differences between because of transfer faults, but roughly speaking, it's related to first opening of the Central Atlantic, North and Central Atlantic, and then opening of the Southern Atlantic, which controlled the eastward first motion of Africa, or Gondwana, because there was also India with it at the time, and Arabia relative to Eurasia, and then a more northerly trend, starting somewhere between 90 and 80 million years. And that corresponds to the opening of the South Atlantic. And roughly speaking, how is the mountain belt? What are the first order characteristics of this mountain belt so that you can see its orientation, width, thickness, or altitude? Well, it's roughly east-west trending. Is it logic? Yes, because with a north-south motion of Africa and India, you would expect a mountain belt that corresponds to collision and shortening in the north-south direction, and therefore an east-west trending mountain belt. We'll see that in the details is much more complex, but first order, that's correct. Its width, is it equivalent throughout from west to east? Well, no, it's much wider here than here. What does that reflect? Well, that reflects the scissor shape motion relative to a pole, an axis of rotation that was further to the west, northwest here, and Gibraltar is much closer to the axis of rotation than Himalayas and Tibet. So there has been, even though the vector of rotation, angular velocity vector might be similar or close, except that it's different here for India because it's been separated from Africa. The linear amount of convergence is much less here than here. So you expect a much wider belt here than here. That makes sense? And also, thicker crust and higher topography here than here. First order, it makes sense. So we're going to go through for today and tomorrow, and even, no, today and tomorrow. Tomorrow. I even Thursday morning. Through different examples. The Alps, which represents an orogenic wedge, triangular shape. Tibet and Himalayas, mostly the southern part, which represents an orogenic plateau. And the Aegean, the hole in the mountain belt, that represents an intermontane basin, a collapsed mountain belt. Well, so let's start now with the general picture of the Alpine Himalayan belt, its constituents and the kinematics and the structure at depth. So the main continental blocks were identified by Argan, always the same guy, was very productive. He published only 2 papers in his life, but very influential. One on the Alps and one on Himalaya Tibet. And you can see here all the cratons, the East Africa, Arabia craton, the India craton, Scandinavian craton, Siberia, and all these are the blocks that are moving relative to each other to form the Variscan belt and then the Alpine Himalayan belt. That's a wonderful map. Huh? So a more modern version of this, still see here for Western Europe, Scandinavia, and the northern part of Gondwana, and also the northern part of Arabia, and the Variscan belt and the Alpine belt. So basically, the Variscan and Alpine belt formed around the same, or in between the same blocks that went up and down, up and down. So that's the same type of map looking towards the east with the same blocks and the different Variscan and Alpine belt. So plate kinematic reconstructions were done looking at all the geological record, look mostly on the 2D. It's a 2D perspective. It doesn't really account for the subductions. But subduction is here identified by high pressure rocks or tectonic accretion of sediments. Actually, these reconstructions mostly rely on sedimentary rocks. So that's 230 million years ago, at a time where Pangaea was still forming one continent, and you had Neothetis, Paleothetis, so that the old ocean, Neothetis, and you recognize the different continents here. So Europe, Africa, Arabia, and Siberia here, and the future Himalaya, Tibet here. So you had the accretion during the Indocenian phase of the Tsongpon Ganze terrain. That's forming the northern part of Tibet. We worked with colleagues on the eastern part of this terrain. And then the start of opening of the central Atlantic, that will start to have Africa moving this way, and opening small oceanic basins in this area at the same time as this one is closing. And here there's a huge Neothetis ocean. So we start to open the central Atlantic, and all these small basins in between Eurasia and Gondwana, and the continental ribbons in between that are going to be the ones that are going to be technically accreted afterwards. So let's play the movie. Get a sense of the motion? Opening of Central Atlantic, closing of smaller. So as the South Atlantic opens, then all these small oceans will start to close. That's the same ones that were opened during the opening of Central Atlantic. And here, India, for some reason, that is something that is also not very well understood in terms of dynamics, separates from Gondwana, and then very rapid convergence towards Eurasia. And that is marked by the Himalayas and Tibet. We do not want to forget Tibet. So we have, during that story, opening of oceans and tectonic accretions of continental ribbons. That's the current day plate kinematics. Well, it's remarkably consistent with the one that has been recorded for the last million years. So it shows still convergence of Africa, Arabia relative to Eurasia fixed, and India also converging towards Eurasia. I won't say much more about that at this time, but it's remarkably consistent. But at the same time, you have motions like this here in the Aegean domain. Gibraltar is going like that, Calabria is going like that. There are some complexities. But the first order in terms of blocks, that's why I'm saying it's important to look at the motion of blocks far from the deformation area. And that's plate tectonics. When you look at in the deformation zone, that's much more complex. And that's not plate tectonics. That's different. I would see the details on it just later. Seismic activity. So here it's a different picture, and you see better. So we see the shallow earthquakes, the orange ones, the ones that are coastal, less than 30 kilometers. But we see also the deep earthquakes from Gibraltar, Calabria, Aegean domain, the Taurides, Zagros, and also Himalayas. You have deep earthquakes everywhere. So subduction and collision at the same time. Coastal deformation and lithospheric deformation at the same time. In terms of topography, so the current topography for Europe is, we see the Alpine, the Western Alps, and there's a hole here, Pyrenees, and there's somehow in a hole here, and then the Gibraltar, the Atlas, Moroccan Atlas, the Apennines. So you see in the details, the nice east-west trend is now broken, much more complex. See the Western Alps, the trend is north-south, perpendicular to the east-west general trend. So it's not well oriented if you compare to north-south convergence. Shortening here is east-west, not north-south. Measured today with structures. So it tells you that there are some complexities and that coastal deformation is not, in these places, easily directly connected to plate kinematics. Calabria Apennines. It's also very odd in terms of orientation compared to the east-west trend. You see here these very rounded shapes. In terms of topography, that's the orogenic front marked by a thrust, but there are also places that are uplifted in the front. So the alpine topography is not only the zone of deformation by structures, it's also uplift of topography in the front. And there are also rifts in this area. Strange to find rifts in these places. Fallen basins at the front of the orogens. These yellow basins are fallen basins, but also large sag basins, basins that are with an axial of symmetry that is vertical, like the Paris basin, that relates to some very big scale, lithospheric scale subsidence. Very, very big diversity of geological features. So how does it look like at depth? And this is thanks to seismic tomography. Everybody has seen seismic tomography. It's a very common way to retrieve lithospheric structure, looking at how the seismic wave propagate relative to an 1D model of reference. So we determine if waves are moving faster or slower. And this gives a map of blue when it's faster than the reference model, and red when it's slower. And geophysicists say that when it's blue, it's because it's stronger, colder, and thus resembles the lithosphere. And when it's red, it's where it's weaker and hotter, probably the asthenosphere. So these are map views. That it's a slice, horizontal slice at 200 kilometers, horizontal slice at 600 kilometers, and these are vertical slices in different places. So we can see at first order is here, there's huge difference between Eastern Europe and Western Europe. Here it's basically the Scandinavian craton. So it's a thick, rigid block, and it limits the Variscan and Alpine orogenies that didn't go beyond that. Then, when we look at 200 kilometers, we see red and blue. So if we try to follow the blue, there's blue here in the Betics, in the Gibraltar, blue in Calabria, somehow in Apennine, in the Alps, and then we have to move in the Carpathians and in the Aegean. But you see, this was used to identify the lithosphere. What is your analysis of this? Well, it says that lithosphere, if it's there, it's discontinuous on a horizontal view. You have plate here, no plate here, almost no plate here, a little bit of plate here, no plate here, and plate here. So it's discontinuous laterally. Strange. Let's look at the cross-sections. That's the Calabrian slab, so it's a cross-section like this. East-west. East-west, and the white spots are the hypocenters of earthquakes. So that's the Wadati-Benioff plain. So there's a good match between the red and blue difference and the Benioff plain. Actually, that's how they tuned their model. You see the color scheme here that is used is very important in the way we analyze the data, right? So the geophysicists, they play with that color scheme until they match the position of the earthquakes so that we could see, us geologists, we could see a lithosphere. Because we're happy to see the lithosphere. And they made the section exactly where the contrast is the biggest, where you have blue and red. They had made the section here, we'd see nothing. You see that, huh? 20 years ago, I told them, hey, I'm interested in these discontinuities, lateral discontinuities. Can we construct a 3D model of that? We're not sure of the data. They didn't want to play with that. So they just wanted to show the plates. Just did the section where you could see the plates. I just came back from EGU, it was last week. Well, now it's in there. 3D views of all this geophysical data, and it's very compelling because it's stimulating and you don't see the plates. You see plates that have been deformed in all over the place. But, okay, let's go back to the basics. They just first wanted to show the plates, and you see one here that is plunging towards the west and is kind of blocked in the mantle transition zones at about 600 kilometers where it flattens. And the fact that there is a red zone here, they interpret it as being related to subduction first like this, and then retreat like that was blocked by the mantle transition zones. I think it makes sense. And the same in Gibraltar, except that it's plunging towards the east and then retreated towards the west. So you have things that went like that. Here in the north, that's illustrated by this section across the Carpathians. You have the Wadati-Benioff plain here, a blue zone that goes down towards the south and is also blocked in the transition zones by something like 600 kilometers. And that's also been interpreted as being related to subduction first like that and then retreat, which allows the asthenosphere to upwell in that region. And last section is across the Aegean. There you have a nice continuous blue anomaly that goes across the transition zones and even down to the core mantle boundary. So there the slab goes down. And it's also being retreated, and we'll see that again tomorrow. So at 600 kilometers, it's a good slice to show all the slab graveyard, all the place where all the slabs have been accumulating, except beneath Aegean, where the plate is going down. So in other words, in that system, you had 3 retreated slabs. 2 were plunging towards the north and then retreated towards the south, and 1 was plunging towards the south and retreated towards the north. So it's something like this, right? Well, one slab is much thicker than the others, but they go like this. You see? And what's the consequence of that? Well, above, in the upper plate, above the retreating slabs, you have opening of basins. And that starts to explain the much more complex situation in these zones. And the retreat of slab is not related to plate tectonics. It's not related to the plate motions far from the zone of deformation. We need to find another force for that. So it's probably one of the good candidates is probably the weight of the slab, where it starts to boom. And that's the time Africa started to converge rapidly and then slow down. So the slab first went fast and then slowed down, start probably to weaken. And, that's my way to look at it. I wanted to show that 20 years ago with the geophysicists. They didn't want to go that way. But last week we discussed that and said, maybe there's some idea to that. We can go back. I'll send you my 3D model. That's my colleague in Italia that told me that. Okay, what about the slabs beneath the Himalaya Tibet? It's a bit more complex. So that's these are sections across. So that's one section. I take this one, north-south, and you see here south-north. That's the Himalayas are here, and that's Tibet here. And there's somehow a blue anomaly that goes down. So that's consistent with what we thought about the tectonics and geodynamics of India relative to Eurasia, with a subduction with a northward polarity. But then it looks like this anomaly is overturned. So the slab is like this. That's also not very well fitting with plate tectonics. Looks like the slab is folded by something that moves the plate faster than what it wants to do. Because if a slab is just falling down according to its buoyancy, it will go like this. If it's going like this, it's probably been pushed by something else that is adding something to the motion. Single overturned slab. And that was also, and we'll come back to that, was also one big surprise from these tomographic images, is to see each time only one slab. Surface geology find at least 1, 2, 3 sutures in some places. And the logic of plate tectonics was each ocean should be closed by one subduction zone, one slab. So 2 sutures, you should find 2 slabs. If there is only one slab for different oceans and different continental blocks, that means that they were part of the same plate. This idea of microplates is kind of not consistent with that. This is one single plate, which could have been oceanic for that part, continental for that part, oceanic for that part, continental for that part. Not sure, huh? But we'll come back to that. At least that's the observation. One slab, different sutures. And in that framework, we have this diversity with orogenic wedges, orogenic plateaus, intermountain basins. So we have, if you have questions now for the general scheme, now we're going to go into the details of the geology. It's okay for the general picture? Even for the bachelors? Yeah? You follow a bit, huh? I think for the bachelors, the idea is not to be able to grasp everything. Is to catch ideas, catch first order pictures, and then this will relate. The problem maybe is that you're going to ask too many questions to your teachers. You say, that's big, strange. We didn't see that with Prof. Van der Haag. Because teachers during the bachelors, I'm helping you, I'm trying to. During the bachelors, we know the idea is to give you something that works well, and is well defined with drawers where we put rocks, and structures that are well identified. But then, as we go further, we know it's not working that very well. So you have to be prepared for that. It doesn't mean that the basic that you're going to be taught is totally wrong, but it's the first order, and then you'll learn that it's not working everywhere. Okay?